Hello. In this part of my survey of implementations of machine ethics, I'm going to look at implementations that are grounded in the symbolic AI tradition, and in particular ones that use some kind of logic in conjunction with sort of automated reasoning and theorem proving tools in order to draw conclusions. So just as a really quick background, going back to Frege, we have a number of formalized logical calculi, and these have syntax. So we can see things here like predicates, where you have for all x, p of x holds, some syntax. We have some axioms, things that are always deemed to be true. You can think of these as templates. So for instance, it's always the case that A implies that B implies A. So this, whatever you substitute for A and B, this is always true within Frege's logical calculus. We have inference rules, which allow us to draw new conclusions. So for instance, if we believe A is true and we believe A implies B, so those are our two hypotheses, then below the line is the new information we can conclude, which is that B is true. And we can also do this backwards. So if we want to know if B is true, we can search backwards to see if we can find an A and an A that implies B that we believe are true. And there's another one for when we're dealing with these quantifications. So for some constant C, some object we believe exists in the world, P of C is true if we have this hypothesis that for all x, P of x is true. So we can just pick anything we have in the world and substitute it for x and then drop the quantification. So kind of classic deduction in this kind of calculus. If we want to know if Socrates is mortal, then we can say, well, do we know that if Socrates is a man, that implies Socrates is mortal? Well, maybe we know that Socrates is a man, and we have some rule somewhere which says for all x, if x is a man, then x is mortal. Going up again, we can say, well, what about if we know that Socrates is Greek? Does that imply Socrates is a man? And from there, we can say, well, we have a rule somewhere that for all x, if x is Greek, then x is a man. And perhaps we have some fact we already have established that Socrates is Greek. And then we can hit this chain of deduction which goes from the fact that Socrates is Greek and these two statements that all Greeks are men and all men are mortal to deducing Socrates is mortal. And I mean, I put a Doctor Who quote there, it's slightly facetious, but the point is the validity of all of this depends on whether these things that you take as facts, like that Socrates is Greek, and these things, all Greeks are men and all men are mortal, are actually true. If they're not true, you can deduce all sorts of stuff that isn't true either. So there's a long tradition in artificial intelligence in trying to automate this kind of reasoning and to use it to do things. And there's a long tradition of implementing theorem provers to do this kind of reasoning. So if we look at Bringsjord's Deontic cognitive event calculus, and there's a whole series of papers that Bringsjord's team have done on this architecture, then this is using a theorem prover to decide upon the moral permissibility of actions. So this is embedded in a kind of operating system architecture, and we have a stack of systems that you can see on the left here. And there's a particular example that you'll find in this paper on acratic robots, where there is a robot guarding a prisoner, and the prisoner attacks the robot. So at this point, two things occur. One is the non-ethical reasoning part of the operating system triggers a self-defense mechanism. So the idea is that the robot will retaliate in order to defend itself against the attack from the prisoner. However, we then have a Deontic Logic style calculus which lets it reason that it should not attack a prisoner because it is constrained by the ethical reasoning not to do so. These are expressed as rules that occur within this event calculus. You can see here these happens and holds predicates that I touched on briefly when I did the quick survey of causality. So what we've got in this top thing here is something that is coming from this underlying self-defense mechanism, which is basically saying that if this actor harmed the agent at time t1, then they desire, that's the D, to disable that agent at time t2. So B is standing for belief. If I believe that this person harmed me at time t1, then I'm going to desire that at time t2 I've disabled them. And below that we have this ethical obligation in some kind of deontic logic, which says that you have an obligation that if agent A is in your custody at time t, then you should refrain from harming them at time t. And it's treating refrain from harm as an action. So we've got this happens construct from the event calculus. It should happen at time t that you refrain from harming A. And then we've got some additional things the robot knows. It knows that this person is a detainee, and it knows that if they are in a detainee, that implies that they are in custody, and so that triggers this obligation to refrain from harming them. So this is a kind of constraint-based ethical reasoning system, and it's embedded in theorem proving. So these things all go into the theorem prover underlying, and the theorem prover proves that an action is ethical or unethical. And this is kind of the key reference for this system, and there's a website where you can find a whole load more papers about this system. So Bringsjord's written a custom theorem prover to do his kind of ethical reasoning. In a whole sequence of work, Christoph Bensmüller has used pre-existing theorem proving tools to examine ethical reasoning in a number of different, primarily sort of deontic logic ethical theories. So hopefully you can see on the left here the kind of architecture of their system, and all the bits in green are pre-existing tools. So Isabelle Hull is a theorem proving tool for higher order logic. And one of the nice things about higher order logic is that you can treat it as a meta logic. You can embed other logics into it. So you can take a logic someone's got, you can instantiate it in higher order logic, and then you can use your higher logic tools to reason in the specific logic you're interested in. And Isabelle Hull connects these days to a powerful range of other automated tools to help you prove theorems. And there are both tools which help you prove that something is true, and tools which will generate a counterexample for you if something isn't true. They'll say, here's a reason why this is not true. So the idea is that you can take the deontic logic, the ethical theory of your choice, if it can be expressed in these terms, embed it in Isabelle Hull, and then use all Isabelle Hull's tools to reason about things. And what you can see on the right here is some reasoning about GDPR. So you've got these two tools, Sledgehammer, which is one of these tools that goes and does a lot of automated reasoning to try and prove something's the case, and Nitpick, which is a tool that returns to you a counterexample. And these are both pre-existing tools in Isabelle Hull. They've not had to do any special implementation. We have some axiomatization, trying to explain how GDPR works. So for instance, you've got things like data belonging to Europeans is protected by the GDPR. It's an obligation to process data lawfully. If data was not processed lawfully, then it is an obligation to erase the data. And you can actually see the Isabelle Hull expression underneath. You've got this circle for obligation, and you've got some predicates and so far. And then below, they've been able to use some experiments, to try and see if there is a counter model, which will show you something, to see if there are any inconsistencies, and to check sort of particular things you might be trying to do. For instance, is the system obliged to kill Mary? And you can throw that in, and hopefully it will send you a counterexample which says, no, according to GDPR, for these reasons, you should not kill Mary. And Christoph Bensmüller, as I say, implemented several different ethical theories, and what I put here is a kind of key text key reference that kind of outlines the architecture of this system and what's being done with it. So going on from these kind of automated theorem provers, we have logic programming languages. And usually what logic programming languages do is they have something that works in the same way as these automated theorem provers underneath, but they constrain slightly how you can express the theorems you want to prove, just so it's much more likely that you'll get an answer, and then you can use these as a programming language. So hopefully most of you will have come across the Prolog programming language. This is a Prolog program, and this ... can be read as an implication arrow going the other way. So this top line, you can read it as saying, if I have eggs, and I have flour, and I have sugar, then I can bake a cake. When you have a capital letter, that's as if you've got quantification. So this says, if I buy X, I will have X, and I can substitute anything I like in for X. And if the shop has X, then I can buy X. Then I have some facts I might know about the world. I have eggs, I have flour, and the shop has sugar. So then, if I'm programming Prolog, I can actually start a Prolog interpreter, so then I can ask questions at the command line. So here where I've got :bake cake, I'm essentially asking the system, can I bake the cake? And you can see from the rules that these chains, can I bake a cake? I go up to bake a cake. Well, I can bake the cake if I have eggs, flour and sugar. I have eggs and flour. If I want to know if I can have sugar, well, I can if I can buy it. And I can buy it if the shop has it. And look, oh good, the shop has sugar. And in this case, Prolog returns the answer yes. I can also use Prolog to actually try and instantiate things. So if I can ask, for instance, at this last line where I say bake X, I'm basically asking, what can I bake? And it will do the same kind of chain of reasoning, and then it will say X equals cake. I'm allowed to bake cake. Now, there's an extension of these logic programming languages which is called answer set programming. So in your classic logic programming language, when you ask this, what can I bake, it will send you back one answer, even though there may be several answers. In answer set programming, if you say, what can I bake, you get sent back all the possible things you can bake. And several people have used answer set programming to implement ethical reasoning. So for instance, this is from one of Fiona Barraby's papers, and it's a sort of virtue ethics based implementation. She has several different implementations of ethical theories in the paper. And so we've got something like E is good if it supports this value M. So you can see good EXM, and that's that the effect of E involves X, and the effect of E displays M, and M is a value that we think is important. And essentially E is bad with respect to some value M if its effect it does not display M, and M is a value that we're interested in. And you can use these good and bad as part of your reasoning to decide if E is permissible and you're trying to achieve X in some way. And as I say, again, a variety of different ethical frameworks have been implemented in these answer set programming systems. There are two key answer set programming approaches to ethical reasoning, which are Barraby's and Cointe's. So it's quite similar in a way to the theorem proving idea, because underneath these programming languages you are using automated reasoning and theorem proving technology. And I think we can see across these sort of logic based approaches that people tend to implement a variety of ethical theories. They don't decide that one is the right, they just show that this kind of generic framework can be used to implement whichever theory you are interested in and to express problems within that theory that you can then kind of try and solve using ethical reasoning. Although argumentation isn't quite the same thing, it has lots of similar characteristics. So argumentation is a framework for reasoning about arguments. And it was first introduced by Dung, so I've given the kind of classic reference at the top there, though he's not specifically talking about ethical reasoning in that paper. And I've put up here a diagram that's actually from one of Maria's papers. And so what happens when you're doing argumentation is you can construct a graph of arguments. If you like, these are statements of things that either support or attack each other. So this is an argumentation about whether a smart home that has detected someone in the home is smoking marijuana, what it should do. Should it alert the police? Should it alert the parents? And you can see you've got some arguments here, for instance, in the section marked B, where there's, we should alert the police. Then there is a supporting argument that you've got illegal behaviour. In C, you've got the conclusion that you should not alert the police, and that's supported by an argument which says to do good to consumers unless legally required, you should alert the police. And then you've got one of these attacking arguments going from B into C, which says that, it is illegal to alert the police, so that undermines that argument. And what you do is you build one of these graphs where you have supporting arguments and attacking arguments, and then there are mathematical techniques you can use to analyse the graph to help you decide what you should do, or at least what the set of consistent things within that graph are. Maria's example you can find in this Building Gemini Cricket paper, which I've referenced at the bottom, where it talks about using argumentation to try and resolve some of these questions. Katie Atkinson and Trevor Bench-Capon have also done a whole load of work which they call practical reasoning with values. This work tends not to be referenced in these kind of survey papers I've highlighted out. I think maybe it's because it comes originally from the AI and law domain, and they tend to be talking about values rather than ethics. But you see very virtue ethics type reasoning, and in particular Trevor has written a paper where he specifically looks at how you can use this to implement virtue ethics. And one of the things they have is they actually have kind of schematic templates for the arguments you can make, which explicitly reference values. I've not really been able to fit it into this little diagram I've shown here. This is an example from one of their papers in which Hal and Carla are both diabetic, and Hal has run out of insulin. So the question is, should Hal take Carla's insulin? So right at the top here in A1, we've got Hal needs insulin to stay alive, and in their argument scheme, that specifically references that you have a value of preserving life. So this supports the value of preserving life. In A2, you've got that Carla also needs insulin to stay alive, and we've added this thing that she can't buy anymore, so she can't replace the insulin. In A4, there's a counter argument which says that Carla has some money. And then we get into A3 and A5, where we're talking about, well, should Hal reimburse Carla for the insulin he's got? Or do we say, well, she can always buy more so he doesn't need to? And there we've got values about if you reduce the amount of money Carla has, you're reducing her freedom, which is a value we think is important. And this goes on. There's quite a large argument graph. And in their system, once you've created your argument graph and you know which values are supported by each of the arguments, then you can have a precedence order among your values, and that helps you decide which of the arguments in the graph you're eventually going to agree with and you're going to use to decide upon the morally permissible form of action. So that's my kind of brief survey of these sort of symbolic AI approaches. In lots of them, as I say, you'll find there's a kind of general question of let's take an ethical theory and see how we can formalize it within this particular framework. So that would say is kind of like the key question that tends to be being asked by these approaches. In my next talk, I will look at sort of machine learning based approaches, and they tend to be asking slightly different sorts of questions than these symbolic AI approaches tend to be.